All right, we're live. So, welcome to today's coffee break. Thank you for being here. I think the last time I presented was in December last year, so it's been a while. My name is Mathieu Bouchard. I'm the product manager for the Eddy Current Array Solutions at Eddyfi, and today I have the chance to be with Ahmed Sweedy, who is our senior application specialist for Eddy Current Array, but also for ACFM Technologies. So today we're going to discuss about eddy current solutions for reformer furnace inspections. Over the past couple of years, we've had to deal with several inspection challenges related to petrochemical plants, and particularly with reformer furnaces. So this is what we'll be discussing today. So before I let Ahmed explain a bit more into details, the fundamentals of a reformer furnace, I just want to introduce the major components here in the presentation that are surrounding the reformer furnace itself. So, as a part of the furnace, we'll be discussing today the reformer tubes, what we can expect in terms of damage mechanism in the reformer tubes, what types of inspection can be done, for the tubes themselves. And then afterward, still discussing the reformer furnace, we will be talking about the inlet manifold that are connected to the furnace, the outlet manifold, but also everything surrounding it. So we're talking about transportation of gases and liquids, so transportation lines, pipelines, stainless steel piping, and finally a word about the storage tank also. So how do we store these elements? So please, Ahmed, I will let you continue from here and just give the introduction on the reformer furnace.
Thanks a lot, Matt. I appreciate having me with you on this coffee break. So, in reformer furnace, we have three major components in the furnace itself. It's the reformer tubes, where the petrochemical products are being processed. And we have also the inlet and outlet manifolds, which connects to the tubes via welds. This is a very important component that connects all and holds all the welds together, holds all the tubes and together via the welds. So this is an important component for inspection because, as we will see in the next couple of slides, the welds itself, it can be subject to damage via several processes, including the heat cycling and the creep damages. I'll let you continue your presentation, Matt, and I will get into more details on the weld inspection of both catalytic and reformer tubes in the next slide. So the inlet and outlet manifolds are connected, as I said, to the both either catalytic tube or reformer tubes via welds. So the welding process itself needs to be inspected to make sure that the weld doesn't have any manufacturing issues, like cracks or a lack of fusion. But also in service tubes, it needs to be inspected regularly to make sure that there is no cracks introduced to the welds via the fatigue process that can be heat cycling, creep damages, any other heating process. We are talking here about a furnace that can be up to 1600 Fahrenheit. The challenge related to that is we have stainless steel welds. We have wall thickness that can be up to half an inch. So the proposed solution for that is the padded prop. The padded prop can, as we will see on our sample now, the padded prop that I have here, it has a nice fitting to the surface of the weld, and it will result in this space fitting between the weld and the prop will result in better detection because you eliminate the lift off completely and you make sure that you follow the profile. The other good thing about the padded prop, it's very small prop that can fit between the tubes, because in the reformer furnace it's not easy access to have it's not easy to have access to the weld itself. So if we can go back to the presentation. The good thing about the padded probe, it can detect surface defects and subsurface defect. When we detect surface defects, we are talking about cracks here, and it can detect 3 millimeter long by 0.70 millimeter deep defects in stainless steel. It can also detect subsurface defects that can be cracks or lack of fusion into the material up to depth of 7 or 8 millimeters, and it can detect also as small as 5 millimeter long by 2 millimeter width defect. Back to you, Matt, to continue.
Yeah. So now if we move over to the reformer tubes themselves, when we talk about reformer tubes, the first question that comes to mind is what type of damage mechanism are we expecting? So the one particular mechanism that represents the main threat for reformer tubes is the creep damage. So creep damage comes from the prolonged exposure to hoop stress, but also stress cycling is what causes the creep damage. So what happens is that very small cavities called creep voids will form within the microstructure of the material, forming the tube. And this is often associated with the precipitates of carbides at the grain boundaries, progressively in number and size through as I said, the high stress and temperature cycling. The cavities become larger and form cracks at the grain boundaries. So this is where it becomes a threat for the asset, for the reformer tube, is when the creep voids are transferred into creep cracking. So we're not talking here about a damage mechanism that is initiated at the surface of the reformer tube, like for example stress corrosion cracking would do. This is really we're talking about a defect that happens inside the wall and progressively progresses through the inner surface to form a complete failure, basically. So the first question when we look at this surface here on the right side and to the type of defect that I've been describing is why don't we use ultrasonics for this inspection? Because we're looking at penetrating the material. We want to find voids, cavities, cracking on the inner surface. So ultrasonics is the main technology that comes to mind. But the reason why surface condition. Those are casting material with a very, very rough surface that is difficult to get good contact with the ultrasonic probes. And this is why there's been a large interest to use eddy currents. We can just use larger coils that remove the effect of the surface condition and just make this inspection much easier. But that being said, using eddy current array for this inspection still comes with its load of challenges. The first challenge is that the material, as it goes through its service life, becomes slightly ferromagnetic with time. And if you are familiar with eddy currents, you know that being able to penetrate a ferromagnetic materials with currents is really a challenge and sometimes even impossible. So here I'll be presenting just after the solution, but the number one challenge is definitely the ferromagnetism of the material. Then the second challenge that we had is that the vertical tubes can be very, very high. So it's not an inspection that is easily done with a manual probe and just scaffolding and having your probe in your hand and scanning the wall. So there's really a need to automate this inspection and make it into a robotic integration. So this is with these two challenges in mind that we have approached this problem, and the solution we came up with was the probe that you see here at the top right corner. So this probe has really large sensors, large eddy current sensors, to be able to have a very strong energy in your magnetic field and penetrate the thick material. And we also use a magnetic saturation bridge on top of these coils. So you can, by using permanent magnets, strong magnets, you will cause the saturation of the material and then remove the effect of the ferromagnetic material, be able to penetrate your material and be able to get ID cracking, but also voids, creep damage that is not breaking the surface either on the ID or on the OD, and be able to just detect it through the wall. And what you see at the top here is from a calibration sample with 20%, 40%, and 60% of depth penetration. So those were just ID EDM notch from the ID side. So even though the wall can be sometimes 14 millimeters, sometimes up to 18 millimeters, and even more. Using these large high energy coils allow us to penetrate the material. And the bottom C scan here comes from an actual reformer tube that had developed creep damage. So what you see here, I don't know if you see it on the image, but you have cracking at different positions. And the C scan that you get here is basically the tube being unwrapped on a two-dimension surface. So it's just a green surface when the pipe is clean, and red indications, red, yellow, orange, like this when you have cracking. So even for someone who doesn't have a strong background in eddy currents, looking at a color mapping like this make it easy to realize that, hey, there's something wrong here, there's cracking over there. So the analysis is really made very simple with this tool. So this takes part of one challenge, which was the saturation, being able to penetrate a ferromagnetic material. The second challenge was to develop, as I said, sorry, I can't access the video here, but was to develop a reformer inspection solution. So what we did here, if my video can start, it will be just a scanner that Eddyfi Robotics has made to allow attaching the ferromagnetic probe on it and then be able to scan vertically. So over the years, Eddyfi has acquired a lot of different technologies, one of them being phased array, MFL, guided wave, but also robotics. So we can integrate these Eddy current probe onto a robotic scanner that will just go up and down the tubes in a matter of a few seconds, maybe.
Hey, Matt, maybe you can enable content to be able to play the video.
Yeah, I'll try to play it after at the end. Yeah.
Okay, no problem.
So the specifications of the probe, here we're talking about a minimum detection of 20% through the wall. So if we're looking for voids, it needs to be at least 20% through the wall thickness. The scan speed of up to 100 millimeter per second. So that's why I was saying it takes a few seconds to go up and down the tubes. Frequency, obviously, with eddy currents, if you need to have a lot of penetration, you need a low frequency. So we're talking about a few kilohertz. And also, we can cover a wide range of diameters depending on what the reformer tube is. So Ahmed, you can continue with this this section here.
Yeah, here's one of the challenges related to the reformer tubes. It's in the reformer furnace, we process a product that has a high carbon content. So inside the tube, there is a high carbon content product that moves inside the tube, while you have a flame on the external surface of the tube, and this flame results in the furnace to reach a temperature that can be as high as 1600 degrees Fahrenheit. So this results in carburization on the internal surface of the tube. If we can look together on the left image here, we can see a healthy tube or the healthy cross section of the tube, and this is a new tube. While when the tube are put in service, so the carburization starts depositing on the internal surface of the tube and creeping inside the material, resulting in rendering the tube brittle. If you look on the right image, right cross section of the tube, you can see that we have about 35% of the wall thickness of brittle material that results in lower strengths of the wall thickness or the matrix of the tube. So this part here results in a risk of having a brittle tube that can shatter and damage and result in shutting down the furnace at a certain point. Therefore, an early detection of this carburization and evaluation is a vital point into the maintenance process of reformer furnace. However, the characterization of the carburization encountered some challenges, including the wall thickness. The wall thickness can be up to half an inch. The reformer tube can be up to a half an inch in wall thickness. Also, when we put the reformer tube in service, there is an oxide layer that forms on the external surface of the tube, and this oxide layer is ferromagnetic, and it results in lower penetration of the eddy current inside the reformer tube, and it's challenging also for the high density of the matrix of this tube. It's challenging also for the UT solutions. So it is not just challenging for the eddy current solution, but also for UT solution. In addition to that, we have different alloys. So in the same reformer furnace, you can have an alloy for the inlet tube that's different from the alloy for the outlet tube. You have OD that's different also on the inlet tubes and the outlet tubes. So all of that to say, we have tubes of height that can be up to 12 meters of different wall thickness, different OD, multiple alloys. So there are lots of challenges. These challenges can be encountered with a solution that integrates robotic inspection so that we can eliminate the scaffolding, which can pose a high risk for the workers or the inspectors. So Eddyfi has been developing robots for some time now. We can inspect up to high to, as Matt showed, will show in the video, the robot is going fast on the tube and can go up to 50 meters of height. And on that robot, it can integrate also an OD measurement system that we develop in Eddyfi and a carburization measurement system. All of that integrated onto one system, into a single scan, single pass scan that can result in an efficient and safe solution for reformer tube inspection. So that's to you, Matt.
Yeah, perfect. Maybe on the everything that is outside of the reformer furnace, but that still needs some NDT, still represents some NDT challenges on the petrochemical plant. One of them is the piping, the large amount of pipe that can be in the plant at a small amount of time. So this is a really simple concept. This is just a standard eddy current array probe, but put into a very large scanner to help having a high coverage and also a high scan speed. So here we're talking about 200 millimeter of coverage around the pipe. So depending on the pipe diameter, you may want to do 4 passes, sometimes 6, 8, 10 passes, depending on the size. And the scan speed also, which is very fast, at 2 feet per second or 600 millimeter per second. So typically the operators won't be walking at that speed anyway, because this is just super fast. So as a replacement for penetrant testing, for example, it can make a huge difference in the time that it takes to detect the cracking, the porosities, the pitting, corrosion. So everything that needs to can be done with the spine. Tolerates some amount of liftoff. So if we're talking about yellow jacket, about epoxy coating, about just coatings that are within a few millimeters of thickness, this can be this can inspect through it. So you save a lot of time not having to remove that coating. For small tubes, the spine that I showed is for 6 inches piping and up. For small tubes, we have this exact same concept. We call it the iFlex. This is just a smaller version of the spine. You can wrap it around with a bracelet like this around very small pipes, and you have a very high resolution to be able, for this example, here on the right side, you can detect about 0.5 millimeter diameter per 0.25 millimeter deep corrosion pitting. So very tiny defects. Everything is adjustable. So if you don't need to detect such small defects, they can be discarded to be able to just see the more important cracking, for example. So Ahmed, you can finish with this this last slide here.
Yes, here is one of the major components also in petrochemical plants are tanks. So we have petrochemical products that needs to be stored in tanks, and the tanks inspection, it part of the tanks inspection is the weld inspection of the tanks. So with high tanks that can be as high as 20 meters, so in this case, you need to install scaffolding around the tank to be able to do an inspection, either with penetrant testing or MPI testing. However, we propose a safe alternative solution for that, which integrates Shark or ACFM products to a MAG HD robot. As you can see in the image, the MAG HD can be integrated with either Shark or ACFM for welding inspection. Both technologies, Shark and ACFM, can detect very small cracks in welds as small as 5 by 0.5 millimeter, and they provide an accurate characterization of both the crack length and depth with an accuracy of plus minus 15%. And this provides a safer solution in terms of the no need for scaffolding. You can inspect up to 50 meter with an easy controllable MAG HD. You can combine also the both the NDT method, which is either Shark or ACFM, that's alternating current frequency measurement on and the visual inspection, because MAG HD is supplied with a camera that has 10 times zoom, optical zoom on that. So all this information is stored in one location and easy access and easy analysis, and also environmental safe, because the penetrant testing and MPI testing, it poses an environmental hazard now. So that's to say, with MAG HD and ACFM or Shark, you have a safer solution and faster also. Back to you, man.
Perfect. So if we can leave the screen up for just a second, I just want to make sure I can have access to this this video here. Yeah, it won't be working this way. So anyway, if you type reformer tube inspection Eddyfi on YouTube on our website, you can find this video. It's just showing the crawler that goes up and down the reformer tubes here. All right, so we can have a look at the questions if there's anything. Okay, so first question we had, well, there's actually a lot. That's good. So can Eddy Current inspect through coatings? I've been discussing it through the presentation, but it really depends on the coating thickness. Basically, if you're using very larger eddy current coils, they have, as I said, a higher energy that can penetrate through the coating more easily. So it's always a matter of trade-off between what you want to detect and what you want to what thickness you have. So as long as you're looking something that is in accordance with the coating thickness, yes, we can penetrate. A lot of stainless steel components on a chemical plants are at high temperature. What are the temperature limitations? So Ahmed, you can probably answer that one.
Yeah, with Eddy Current solutions, we have developed solution that can work up to 200 degrees Celsius on the chemical plants. We are working now on developing higher temperature solutions, either with Eddy Current and also with Eddy Current Arrays. But also we have another alternative, for example, for welding inspection, that can be ACFM, that can work up to 500 C as well. So that's to give a quick answer to that.
Perfect, thank you. Do you have a solution to inspect cracking tubes? Yeah, so I haven't talked about it, but the cracking tubes, they are very similar to the reformer tubes in terms of the damage mechanism. So they can have the same creep damage and temperature cycling issues, but on top of it, they also have an oxide layer that is ferromagnetic on the OD. So the same type of partial saturation using permanent magnets can help saturate the oxide and penetrate also. What is the highest depth penetration for this ECA? This is customizable. So again, it will depend on the size of the sensors. If you're looking for, let's say, 1 millimeter crack, so something very, very small, there will also be very little penetration. But if you're looking at creep damage, for example, that is usually very significant, we can penetrate up to 20 millimeters sometimes. So very almost close to 1 inch of penetration. Is it both circumferential and axial crack? Yes, absolutely, absolutely. All our eddy current probes, they do at the same time in the same scan, they do both circumferential detection and axial detection. You don't need two scans. This is done at the same time. What would the cracks look like? If you can display my screen again, Jean-Philippe. So on the presentation here, this is what I was showing. So basically, you're looking at the C-scan, so a 2D color mapping, and the cracks will show up as red and orange indications here. So in contrast to a green background, you have the indications in red. Please share more details about robotic solutions for reformer tubes. Yes, absolutely. I'll try. Ahmed maybe can answer the next question, and I'll pull up the video in the meantime.
Okay, no problem.
That was the last question that we had for now, guys. That's fine.
Just give me a moment. Okay, I think I finally have it. If you can share my screen just one more time. All right, here we go. So again, all this is depending on the outside diameter. So we can make probes adjustable. You can use the same type of crawler for different OD of pipes, but the idea is really to put the probe in good contact and move along the height of the tube. And this is all offered by Eddyfi, so you don't need to have a separate integrator for the robot. All right, excellent. So thanks everyone. Thanks Ahmed again for helping me with this coffee break. If there's no more questions, you can contact us. Our email addresses are at the bottom, so make sure you contact us. And yeah, thank you for being there. Have a good day.
Thank you so much, Master, for having me. Thank you. Appreciate it.